Okay, this is a revision video talking about floating point representation using binary numbers. So we always refer to the acronym M-A-R-E, or MARE. Okay, and this is short, or this stands for mantissa, accuracy, range, exponent. And basically, if I draw a line between those two things, that just shows you that if you want to increase the accuracy of a floating point number, you have a larger mantissa, and if you want to increase the range of numbers that you can represent in floating point, you increase the exponent. Now here's an example of a decimal mantissa and exponent. So the mantissa could be 246 times 10, because it's base 10, to the power of the exponent, so that is 4, for example. Now there's a decimal point at the start there, don't forget that, I did there. But in that decimal example, that basically is the numbers in your calculation, in your floating point calculation, and the exponent is the number of spaces to push that number to the left. Okay, so you would end up with 246 being pushed 4 places to the left, which would result in 2460. Okay, because it's being pushed 4 places to the left, so there's another 0 to be added in there. Okay, that's the decimal. So if, for example, we wanted to store a decimal number, I mean that last example wasn't a decimal number, we want to store a number such as 12.5, okay, using floating point representation. In a computer, what we have to do is we first have to work out the binary value of the mantissa. So 12.5, we'll just draw a grid. Okay, so again, 1, 2, 4, 8, 16. I'm just going to stop there because we're only representing 12, so we don't need to go any further than that. But remember, if you go past the decimal point, you then start to half. So it's 1/2, 1/4, 1/8, 1/16, and so on. There is no 0, remember that. So if I just draw my grid lines just to show you where everything is going to go. "16 is too high, but 8 fits into 12, so there is 4 remaining. There's the 4. Okay, so we've got 0.5 remaining. Doesn't fit into that, doesn't fit into that, but 0.5 is a half, so it fits into that. Now, I've got a decimal point there, but that really should just be a line. Okay, and because there's nothing left, these don't have to have value, and we wouldn't use those. Okay, so don't feel you have to put trailing zeros at the end. If I have to write that out now, that would be, let's start at number 8, because that's the first one with a digit. 1, 1, 0, 0, 1. Okay, so that is our binary value of our mantissa. Okay, so the number that we're representing, including what's after the decimal point. The next step is to work out how many places to the left that number has to be pushed. Okay, because remember, our mantissa will start with a decimal point. So, how many spaces or places the number moves to the left. Now, if we want to represent that number, our decimal point has to move. Let me just change pens for a second. Our decimal point has to move to there. So that's 1 space, 2 spaces, 3 spaces, 4 spaces to the left. Okay, so the numbers have to move 4 spaces to the left to get into the right, get back into its original sequence. Okay. So it's 4, but 4 is not a binary number, so you convert it to binary. And 4 in binary is 1, 0, 0. So we would write out this last step, like this. So the mantissa times 2 to the power of the exponent. So our mantissa is 0.11001 times 2 to the power of 100. And that is how we represent 12.5 using floating point representation.